in bulk, they are small in size, and they have very fast switching speeds. So the operation is very fast. Digital circuits are also called as switching circuits because the voltage level in a digital system changes from one value to another almost instantaneously. This transition time from one voltage to the other voltage is zero. Digital systems are not affected by electrical noise, by the temperature, and by the age of components, and the noise immunity is very high. Digital systems are suitable for processing numeric as well as non-numeric data. We do not only do calculations with our data, but we also process video, audio, and text. And this can be easily done by digital systems because ultimately all data is converted into a series of zeros and ones. Digital systems are economical to design and they can be mass produced. Of course, integrated circuits are available in a logic family. So within a logic family, all devices will have similar characteristics. So this will make it easy to interface devices, connect one device to another, and therefore you can build larger complex systems. This permits scalability, much like uh, maybe a Lego toy. So digital circuits are also called logic circuits because each type of digital circuit that is constructed, it has or it obeys a certain set of logic rules. So the manner in which a circuit responds to its input is called as the circuit's logic. So for example, one may have a circuit whose output is high or 1 only if all inputs are 1. We'll study about such circuits in this course. Digital circuits have a very important property which is of memory. So they can remember the last state they were in. That means 0 or 1. Now this property is extremely useful in devices like computers, telephones, calculators, watches, medical devices where data has to be stored and has to be processed again. The very important advantage of digital systems is that data can be displayed in a convenient way on very large display panels, or it can be adjusted on smaller displays as per the requirement. Digital systems are also more accurate and precise because they can be expanded to handle more digits, and all we need to do is add more switching circuits. So as we said in the previous point, that these circuits can be built by joining them one after the other, and therefore more precision can be obtained. Some digital signals carry extra information that allows damaged data to be repaired at the receiver. So although digital signals are not easily affected by electrical noise, if a signal is affected or if it is damaged due to some unwanted data or unwanted noise or unwanted signal, then this damage can be taken care of at the receiving end. So this extra bit of information that our digital signals carry can be, for example, what is called as parity information or parity data. So here are the summary of advantages of digital systems. There are very few operations and hence it is easy to understand the working of digital systems. They provide a better noise tolerance. They are not easily affected by external noise, and by noise here we mean electrical noise, that means unwanted signals. They are lower cost and easily they can be fabricated. They are more reliable, they are not affected by temperature and other factors. The power consumption of digital circuits is much lower. They are small in size, which means that these systems can be portable. Scalability is easier, which means that systems can be joined one after the other and we can have more complex data processing. These are ideal for data communication over long distance. This again comes because the signals being digital signals are not easily affected by external noise. You transmit signals over large distance. We can use repeaters instead of amplifiers. They can operate over a well-defined dynamic range. linearity is not required. What it means is, so in a digital world, why do we need an analog signal at all? Require these. So although digital signals have many advantages, the fact remains that the real world is mostly analog. This is the major drawback of digital signals. For example, temperature, height, pressure, force, acceleration, wind velocity, these are all analog quantities. These are continuously varying quantities. So for example, the temperature of a room will vary continuously, not from one level abruptly to another level. So we must take these analog quantities and we must digitize them or convert them into a digital form and then process, preserve and propagate these digital signals. So this conversion of an analog to a digital form is done by an A to D or an analog to digital converter. So for example, here we have an analog signal which could be, for example, voice, which is converted through an A to D converter and it gives us a digital signal. You can observe here that on the left side we have the analog signal which is continuously varying. It has different voltage levels, different amplitude levels, but on the right the digital signal has two fixed values which are either a 0 or a 1. And at the receiving end, this digital signal has to be again converted by using a D to A or a digital to analog converter back into the analog signal. So what are the disadvantages of digital signals? So the conversion of real world analog signal to a digital signal and then again processing that digital signal, converting it back into analog, time consuming. Certain systems that we use will have both analog and digital systems, and such systems are called as hybrid systems. So we have seen what are the advantages and disadvantages of digital signals.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
In this session, we will discuss the conversion of decimal number to its equivalent binary value. Now, in the decimal number system, we have seen that the symbols that are used are 0, 1, 2, 3 up to 9. And since there are 10 symbols, we say that the base or radix of decimal number system is 10. In the binary number system, only two symbols 0 and 1 are used, and so we say that the base or radix of the binary number system is 2. The binary number system does not use symbols like 2, 3, 4, etc., and therefore those are not valid in the binary number system. Let us understand what is meant by LST and MST in a decimal number system. LST stands for least significant digit and MSD stands for most significant digit. To understand this topic, let us consider a decimal number 572. There are three digits 5, 7 and 2. Now this number 572 can be written as 500, which is the first part, then plus 70 and plus 2. Now 500, we are writing it as 5 times 100. In fact, that is why we pronounce it as 500. It is as if it is 5 hundreds. Plus 70, we are breaking it up as 7 into 10. So it is 7 times 10. And plus 2, we write it as 2 into 1. So from our school mathematics, we will remember that we say that this number 2 is in the units place. So we say that 2 is in units place, and the reason for that is that it is multiplied with 1. But the number 5 in this particular example is in hundreds place because it is multiplied with 100. So this is our value 572. Now you'll observe that this has been written as 5 times 100 and plus 7 times 10 plus 2 times 1. And here the digit 5 is multiplied with 100, which in powers of 10 we can say it is multiplied with 10 raised to 2. Similarly, digit 7 is multiplied with 10 raised to 1, and digit 2 is multiplied with 1, and that 1 can be written as 10 raised to the power 0, since we know that any number raised to 0 is 1. Now 5 is multiplied with the highest weight here, and that is 100, and therefore we say that 5 is the most significant digit. And if we look at the digit 2, 2 is multiplied with the lowest weight of 1, which is also 10 raised to 0, and we say that the least significant digit is 2. So in this number 572, 5 becomes the most significant digit. It is a digit with the highest weight, whereas 2 has a weight of only 1. So we say that this number is a positional numbering system, because if we change the position of any digit, then the value of that number changes. So in a positional numbering system, the position of a digit decides the value of that digit. Now let us take an example to convert a decimal number to its equivalent binary value. The method is outlined here, and as we go through this one step at a time, we will see how to convert this number 23, which is in the decimal system, to its equivalent binary value. So we have made here 3 columns, and in these 3 columns, in the first column we will write down the multipliers, that means 2, the divisors 2. Then we have the number that we want to divide. This number appears in the central column. This is the number that has to be converted, and in the last column we will write down the remainders, and these remainders will give us the bits of the binary number. So we'll start by first dividing the decimal number 2 by 2, and therefore I'll write here divisor as 2. 2 now goes 11 times in 23, so 2 11 times 22, and that leaves us with a remainder of 1. So we have these 3 steps. So we got the remainder, 2 11s are 22, and the remainder is 1. Now in the next step we will continue with division of this quotient by 2, and we'll continue this till the quotient becomes 0. So now we will just take this 11 as our quotient and divide it by 2. So again 2 5 times is 10, that leaves us a remainder of 1. Since this quotient is not yet 0, we will again divide this by 2. 2 times is 4, that leaves us with a remainder of 1. Now 2 again divided by 2, because this is not yet 0, so 2 1 times is 2, that leaves us with no remainder, so we write 0 as the remainder. This quotient is still not 1, it is still not 0, and therefore we again divide this by 2. So 2 0 times is 0, and that leaves us with a remainder of 1. Now you can observe that the quotient has become 0, so we will now consider the remainders in the reverse order, and our binary equivalent becomes 1. This becomes the most significant bit, then 0, that is our next bit here, then 1 1 and 1. So those are the 3 remaining bits, and this becomes the binary equivalent. Now when we pronounce this, or when we read this, we read it as 1 0 1 1 1. Now that we have seen what is LSD and MSD for a decimal number, we also have what are called as the LSB and the MSB of a binary number. Let us consider the number 10111. This is a binary number which we obtained in the previous example. This number has 5 bits. These are the 5 bits of that number, 1 0 1 1 1. Now out of these 5 bits, the bit which is at the extreme left, that means the bit 1, this bit is called as the most significant bit. This is similar to the most significant digit, which was the digit at the extreme left of our number. The the rightmost bit, which is in this case 1. This rightmost bit, we will call it as the least significant bit. Now observe this. What is the significance of these terms, most significant bit and least significant bit? A change in the least significant bit will not change the value of the original number drastically. The bit can be either 0 or 1. So let us assume that our original number is 10111. The decimal value of this number is 23. If we change the least significant bit from 1 to 0, we get the number 1011, and here is the bit which was originally 1 in our number. Now we have changed it to 0. Now if we convert this number from binary to decimal, we get the decimal equivalent as 22. So by changing the least significant bit, the value has changed from 23 to 22. It's not a very significant change. But observe what happens if we change the most significant bit from 1 to 0. Again, here is our original number 10111. If the most significant bit is changed from 1 to 0, in the original this was 1, if it is changed to 0, and we keep the other bits as they are in the original, so the other bits remain there same, and now if we convert this into the decimal equivalent, this gives us the decimal value 7. There you can see there is a drastic change in the value of the number, and therefore the most significant bit has the significance that its value decides the value of the number. If this value changes from 1 to 0 or 0 to 1, the final number can change drastically. Now in this example 2, let us consider the conversion of a decimal number to its binary equivalent, and we'll use another method. So in this method, we will first write down all the powers of 2, and we'll start from the power of 2 raised to 0, and we'll keep on writing the powers of 2 from right to left. So 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and we will come up to 2 raised to 7. Now below that we will write the values of these powers. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, and till we reach here 2 raised to 7, which is 128. Now these powers of 2 are actually simple to calculate. Just we need to remember that 2 raised to 0 is 1, and from here on we just keep on multiplying each of the values 1 multiplied by 2. So 1 into 2 gives us 2. Then we multiply this 2 again by 2 to give us 4. Again multiply this 4 by 2, so that gives us 8. 8 into 2, 16. 16 2 times 32. 32 2 times 64, and 64 2 times is 128. So it's very easy to get these values. Now let us understand how do we fill up the values in these cells for the binary digits. We start with our number 73. We will compare this 73 with the value 128. If the value 73 is less than the value given here, we will put a 0 in the binary digit cell. Again we compare 73 with the number 64. 73 is greater than 64, so we'll write a 1 bit, and 73 minus 64 gives us 9. Now we will compare 9 with 32. So now our comparison is of 9 with 32. So 9 is less than 32, so we put a 0. Now we compare 9 with 16. So 9 is less than 16, so put a 0. Again we compare 9 with 8. So 9 is greater than 8, so we put a bit 1. And now the value that we have is 9 minus 8, which is 1. So now we compare 1 with the next value. So 1 will be compared with the value 4. 1 is less than 4, so we put a 0 bit here. 1 we compare it now with 2. 1 is less than 2, so we put the bit 0. Now we compare this one with 1. 1 is equal to 1, so we put the bit 1, and therefore now we have reached the value 1 minus this value 1, which is equal to 0. And now we consider these bits, binary digits, in the forward order, and therefore our binary number becomes 0101. This is the first part which we have considered. So all these values 0101, 0100, followed by 1001. Those are the values that we have obtained here as our binary number. And when we read this number, we read it as 01001001. Let us now understand how to convert a fractional value to the binary value. Let us, as an example, take the fractional number 0.3125. This is a decimal number with 4 decimal places. This has to be converted into the binary. Now, the method is outlined here in the box. So the method is, we will keep on multiplying the given number with 2. So multiply the fractional part by the decimal number by the number 2. So in the first part, we will take 0.3125 multiplied by 2. This gives us the value 0.6250, and because there is no carry, we write the carry as 0. So when you multiply 0.3125 multiplied with 2 gives us 0.6250. Since there is no carry, we write here. Then we take this fractional value and use it as our next number. So we have as if taken this fractional value, and now we will again multiply it by 2. Now observe this part. 0.6250 into 2 will give 1.2500. So the 1 we write it as a carry, and fractional value becomes 0.2500. So we will again continue this. 0.2500, this part has been brought forward, and now multiply this by 2, so that will give us 0.500. When you carry out this multiplication, there is no carry, and therefore we will write here a carry of 0. Now we will take 0.500 again, we will copy it into the number column. So 0.500 multiplied by 2 will give us 0.0000 with a carry of 1. And now these carries, we consider them in the forward order, and therefore our decimal value 0.3125 is equivalent to 0. So you have 0, 1, 0, 1. Those are the 4 bits. This point that we have here is called as a binary point. We will call this as a binary point because it is a part of a binary number. This is of course analogous to the point that you have here. We call this as a decimal point because it is a part of a decimal number. Now let us consider how to convert a mixed number like 23.3125 to its binary equivalent. Now this 23.3125, you can see, has been broken up into 2 parts, an integral part 23 and a fractional part of 0.3125. So the first part of converting this number 23.3125, converting into the binary, will involve 2 steps. In step 1, we will convert the integral part 23 to its binary equivalent. This we have seen in the earlier case, 23 of decimal. We saw in the earlier example is 10111 of binary. In step 2, we will convert the fractional part 0.3125 to its binary equivalent. So that was 0.3125 is 0.0101, and therefore our final answer 23.3125 will consist of the binary equivalent of 23, which is 10111. We got that value here, followed by the binary point, and then 0.3125, it has the binary equivalent of 0.01.01. 0101. So that is the one value we have shown, and therefore this is the complete answer for 23.3125.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
In this video lecture, we will see how to convert a binary number to its decimal equivalent. Let us take the first example in which we have to convert the number 10111 from binary to its decimal equivalent. Now the first step in doing this conversion is to identify the least significant bit and the most significant bit. So our given number is 10111. Now the rightmost bit is the least significant bit because it has the smallest weight. The bit at the extreme left, that is this one, is our most significant bit because it has the highest weight. Now, having done this, we will first make a table of 3 rows. Our first row contains the powers of 2. Here, we have started from the right. We start with the powers of 2. So 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and we go up to 2 raised to 7. Now, for this particular problem, we will not require up to 2 raised to 7, but this is a general explanation which can be used for any problem which involves up to 8 bits. Now, in the next row, we write down the values of these powers of 2. So 2 raised to 0 we know is 1, 2 raised to 1 is 2, 2 raised to 2, 4, 2 raised to 3, 8, and like this, we have 2 raised to 7 is 128. Now, the third row, we will have the bits. Now, let us observe how to fill up this bits row. Starting from the least significant bit, we will start from the least significant bit, and that is why this has been highlighted here. What we will do is we will write each bit below the corresponding power of 2. So as we said, this is the least significant bit which has the smallest weight. So we will write this bit under the power of 2, that is 2 raised to 0. So we bring this bit here 1. The next bit in our number is 1. This is the bit with the next higher power, and therefore we now bring this bit to 2 raised to 1, that is 1. The next bit is again 1, that is copied under 2 raised to 2, that is the value 4. So this bit has the weight of 4. The next bit in our number is 0, which is written under 2 raised to 3. That means the value of this bit or the weight of this bit is 8. So we write 0. And the most significant bit, we put it here under 2 raised to 4, that is 16. So all our bits have been copied, and since there are no more bits left, we will just pad these remaining powers of 2 with zeros. Now all the bit positions have been allotted, and so our given binary number can be written as 0 into 128. Now this 0 is the bit at the extreme left. This we multiply it with 128. So this is 0 into 128. Then similarly 0 into 64. This is 0 multiplied by 64. That gives us the next. Then 0 into 32. 0 into 32. Then plus 1 into 16. So we have the bit 1 multiplied by its weight 16. 0 into the weight 8. 0 into the weight 8. So at each position what we are doing is we are multiplying the bit, that is say this bit, with the appropriate power of 2 or the value. So 1 into 4, so that is 1 into 4. Then we have the next bit 1 into 2, so 1 into 2, and the last bit is 1. We multiply it by its weight 1, so that is 1 into 1, and therefore this becomes 0 into 128, that is 0, plus 0 into 64, 0, and like this we have 1 into 16, you can observe, is 16. 1 into 4 is 4, and therefore we have the given binary number as a sum of these values, and this can be written as 0001 0111 of binary is equivalent to 223 of the decimal. So these three zeros that we see here at the extreme left, these have been padded to create an 8-bit binary number. So these were not really necessary, but in case we come across an example where 8 bits have to be used, then we know that we must go up to 2 raised to 7. Let us take the next example where we have to convert the binary number 10010 to its decimal equivalent. Again, the steps will be similar. First, we identify the least significant bit. So 10010, this becomes the least significant bit, the bit which is at the extreme right. So this is the bit which is at the right, and we have the most significant bit, that is the bit at the left. So we have identified the bits. Again, as in the previous example, we make a table of 3 rows. The first row is powers of 2. So starting from the right, we have the powers of 2, 2 raised to 0, 2 raised to 1, 2 raised to 2, and like this we go up to 2 raised to 7. Below that, in the next row, we write down the values of these powers. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, and so we have up to this 2 raised to 7 is 128. Now again in this, the third row will contain the bits. So we will pick up each bit starting from the least significant bit and put it below the appropriate power of 2. So since this is the least significant bit, it has the smallest weight, we copy this bit under 2 raised to 0, so that is 0. The next bit is 1, so we copy this bit under the power of 2 raised to 1. Our next bit is 0, that will be copied under the power of 2 raised to 2, that is the value 4. The next bit I have here is 0, so we copy it under the power 2 raised to 3 with value 8. And the last bit, the most significant bit in this example is 1, so that is copied under 2 raised to 4, and that becomes 1. Since all the bits have been used up, we just pad the remaining bits with 0. And again, in this example, our number is 0001010. It's the same number, but we have padded these 3 extra bits. These are the 3 extra bits. So you have 000, that explains these 3 bits, followed by 10010. Those are the remaining bits. This is equivalent to, now let us see, we again multiply each bit with the corresponding value. So 0 into 128 plus, we'll have 0 into 64 plus, we have 0 into 32 plus 1 into 16 plus 0 into 8 plus 0 into 4 plus 1 into 2 plus the 0 into 1. So we are multiplying each bit with the appropriate power of 2, and this can be written as 0 into 128 is 0, 0 into 64 0, 0 into 32 0, 1 into 16 is 16, plus 0 into 8 is 0, plus 0 into 4 is 0, plus 1 into 2 is 2, and plus 0 into 1 is 0, and this is equivalent to 18 of decimal. So this is how we can convert a given binary number to its decimal equivalent. Now here is an important observation about binary numbers. Let us take the examples we solved earlier. This was the first example, 10111, and we saw that its decimal equivalent is 23. The next example was 10010, and its decimal equivalent was 18. Now observe this. In the first example, the least significant bit was 1 and the equivalent decimal number was an odd integer. So we have an important result. If the least significant bit of your binary number is 1, then the equivalent decimal value will be an odd integer. Let us take the next example where our binary number was 10010. Here the least significant bit was 0. The binary equivalent, the decimal equivalent of this was an even number, and therefore here is our result. If least significant bit is 0, then the equivalent decimal value is an even integer. Now this, you will realize, is somewhat similar to what happens in the decimal numbers. We know that any number which ends with 0, 2, 4, 6 or 8 is an even number. So for example, number like 12, 16 or maybe 24, 18, 30, all numbers ending with 2, 4, 6, 8 or 0 we say are even numbers. And if a number ends with 1, 3, 5, 7 or 9, is we say it's an odd number. So we'll have numbers like say 23 or 31, 45, 67 or 89. All such numbers we say are odd numbers. So in a similar way, the important result is numbers, binary numbers in which the least significant bit is 1, we say that the equivalent decimal value will be an odd integer. And if the binary number has the least significant bit as 0, then we'll say that the equivalent decimal value is an even integer. Now this result is important and it can be sometimes used to check our answer when we convert from a binary to decimal or from a decimal to binary. Let us now take up an example of what happens with fractional binary numbers, fractional decimal numbers, decimal numbers which have a value less than 10. Now let us consider a number such as 0.142 in the decimal system. Now this number can be broken up as a sum of 3 parts. So we have 0.1 plus 0.04 plus 0.02. So we can see that this can be broken up into 0.1 plus 0.04 plus 0.002. Now this part can be written as 0.142 can be written as 1 upon 10. So 0.1 is 1 upon 10. 0.04 can be written as 4 upon 100 and 0.002 can be written as 2 upon 1000. That means we can write 0.142 as 1 into 10 raised to minus 1. So you have 1 upon 10. When the 10 is taken up in the numerator, we have 1 into 10 raised to the power minus 1 plus 4 into the power 10 raised to minus 2 plus 2 into the power 10 raised to minus 3. So the important result here is that any number less than 1 can be written as a sum of the products of the digit and the multiplier, appropriate multiplier of 10. So since this is the first place, 1 into 10 raised to minus 1. Since 4 appears in the second place after the decimal point, we have 4 into 10 raised to minus 2. Since 2 appears in the third place after the decimal point, we have 2 into 10 raised to the power minus 3. Now this result, we will use it when we convert a fractional binary number to its decimal equivalent. Let us take this example of converting the binary number 0.1101 to its decimal equivalent. Now, just as in the previous case where we were dealing with decimal number, we can write 0.1101 as 1 into 2 raised to minus 1. Why we take 2 raised to minus 1? Because since we are dealing with the binary number system, this will become 1 multiplied by the base of this number system is 2. So 2 into 2 raised to minus 1 because this is the first decimal place. Then we have plus 1 into 2 raised to minus 2. So why 2 raised to minus 2 we take here? Because this 1 appears in the second position after the decimal place. So 1 into 2 raised to minus 2. The next digit we have here, the next bit we have here is 0. So this will become 0 into 2 raised to minus 3. The next bit that we have here is a 1. So we have 1 into 2 raised to the power minus 4. And therefore, now this example is dealing with the uh, fractional values of a binary number. Now we can observe one thing, that this 0.1101, if we write this number, then this point 1, the bit 1 here becomes the most significant bit, whereas the bit 1 here is the least significant bit. And therefore we now again make the table of powers of 2, the value and the bit. Only now the difference is when we make the power of 2, as we go from left to right, the powers of 2 keep on decreasing. So we have 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, and so till we have 2 raised to minus 7. The values of these powers, 2 raised to minus 1 is 0.5, 2 raised to minus 2 is 0.25, 2 raised to minus 3 is 0.125, etc. till we have 2 raised to minus 7. Now let us observe. We take each bit from our fractional number. So starting from the most significant bit, we put the bit under the appropriate power of 2. So we have 0.1, so the bit is 1. So we put the bit 1 under the power of 2 raised to minus 1. The next bit is 1. This bit is written under the power of 2 raised to minus 2. The next bit, that means the bit in the third position after the decimal point, we put it as under the power of 2 raised to minus 3. The fourth bit after the decimal point, we put it under the power of 2 raised to minus 4. And since there are no more bits, we just put these bit positions as we put these bit values as 0. And therefore our given number 0.1101 can be written as equal to 1 into 2 raised to minus 1 plus 1 into 2 raised to minus 2 plus 0 into 2 raised to minus 3. Here it is, we can see this, plus 1 into 2 raised to minus 4, etc. And therefore this can be written as equal to 1 into 2 raised to minus 1 is 0.5, so 1 into 0.5 plus 1 into 0.25 plus 0 into 0.125 is 0 plus 1 into 0.0625 and this 0 into 0.03125 0 plus the next number also will be 0 and the last 0 into this also gives us 0, and when we add this we get 0.5 plus 0.25 plus 0.0625, that gives us 0.8125, and therefore the given decimal number in binary can be written as 0.8125 of the decimal system. Now let us see how to convert a binary number like 10111.1101 to its decimal equivalent. We will observe that this binary number has an integer part, that is before the decimal, so it has an integer part, and it also has a fractional part, or it has also got a part after the binary point. So this we can say is its fractional part after the binary point. Now to convert this type of a number into its decimal equivalent, we first take the integer part, that means the part before the binary point, and we convert this number into its equivalent decimal. So this we already seen in the first example, how we convert an integral binary number into its decimal equivalent. Then we take the fractional part 0.1101. So we have the fractional part or the part after the decimal, after the binary point, and we convert it into its equivalent decimal. So we saw in the earlier example that this is 0.8125, and therefore the entire number can be written as the integer part, which corresponds to 23, and then the fractional part of binary corresponds to 0.8125. This becomes our complete equivalent value in the decimal system.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
This is a lecture on decimal to octal number conversion. Now, the decimal number system uses 10 symbols 0, 1, 2, 3 up to 9. And since there are 10 symbols, we say that the base or radix of the system is 10. The octal number system, on the other hand, uses symbols 0, 1, 2, 3 up to 7. That means there are 8 symbols used in this system, and therefore the base or radix is 8. We'll see that symbols like 8 and 9 are not valid in the octal number system. Let us see what is the advantage and disadvantage of octal numbers. The major advantage of octal number is that a set of 3 bits or binary digits can be represented as a single octal digit. This leads to a more compact notation. For example, consider a binary number 101. This occupies 3 bits, but the same number can be represented by the single symbol 5 in the octal number. In another lesson, we'll be learning how to convert from octal to binary and vice versa. But octal numbers have a disadvantage in that a computer system doesn't really understand octal numbers. The native language of a computer is the binary language. Let us now take one example of how to convert a decimal number to its octal equivalent. The method is outlined here, and we'll go through this one step at a time to understand how to bring about this conversion. So we have a decimal number 295. This is our original number, and this 295, since it is in the decimal system, we have represented it as 295 with a subscript of 10, and we want to convert it into the base 8, and that is why the subscript shown here is 8, and this is the number that we need to calculate. Now the method is very simple. We will create 3 columns here. The first column will contain our divisor, which is going to be 8. The second column contains our original number. This original number that we have is 295. The third column we have marked as remainder. Now let us start by understanding how we bring about this conversion. We will divide the decimal number by 8. The number that is given to us is 295. We will keep dividing this by 8. So 8 goes 36 times and the remainder is 7. So 8 3 times is 24. That leaves a remainder of 5. That leaves a 5 remainder, and 8 6 is 48, which leaves a remainder of 7. So we have a remainder of 7 right now, and the quotient that we have is 36. Now we will continue this process till we get a quotient of 0. So we'll go back and we will repeat this step where we divide the decimal number again by 8. Now our decimal number now is 36. So 8 4 times is 32, and that leaves us with a remainder of 4. Since the quotient is not yet 0, we'll again go back and divide this by 8. Now observe this. 4 is less than 8. So 4 cannot be divided by 8. So we'll say 8 0 times is 0, and that leaves us with a remainder of 4. Now the quotient has become 0. So we will take all these remainders in the reverse order, and we will get the number 295 of decimal. It can be expressed as the number 447 of octal. One must be careful here not to pronounce this as, not to read it as 447, because this is not really a number in decimal, it's in octal number system, and this becomes your final answer. Let us consider another example here, which is to convert a decimal number to its octal equivalent, and the number that we have is a fractional value of 0.3125. Now, we make four columns here. The first column is having the title number. The second column, we mark it as multiplier. The third column, fractional value, and the fourth column is carry. Now, we will write down the original number given to us 0.3125 in the first column. In this column, we will write down 8. So, we are multiplying the number 0.3125 with 8. When we carry out this multiplication, we get the fractional value 0.500 and the carry is 2, because 8 times 0.3125, this is 0.3125 times 8. This is going to be 8 5 times is 40, 0 with a carry of 4, 8 2 times is 16, and 4 is 20, 0. This is 2, 8 1 times is 8, and 2 10, 0 with a carry of 1. 8 3 times is 24, plus 1 25, so 5, and with a carry of 2. So we get 2.500. So the fractional part of 0.500 we have written here, and the carry is shown here in the last column. Now we will continue this process till we get a fractional value of 0. So we will copy this value 0.500 into the first column. So this value, we bring it down into the first column, okay, and again continue with the multiplication by 8. So 0.500 multiplied by 8, this is 0.0000, but of course there is a carry of 4. So we have here 0.5000 multiplied by 8. So this is 80, 80 times 0, 80 times 0, 85 times is 40, 0 with a carry of 4. So we write the fractional part 0.00 in the column here, and the carry becomes 4. And now since we have the fractional value of 0, we can stop the process. We consider the carry values in the forward order, and our final result becomes 0.3125 of decimal is equivalent to 0.24 of octal. Let us now consider a mixed number. In this number, we have the decimal value 295.3125. Now, this number conversion can be done by using the methods of the previous two examples. So, the first part 295, we separate it out, and this 295 of decimal, we convert it by the previous method, and this becomes 447 of base 8. We did this in the first example. Now we convert the fractional part 0.3125, this 0.3125, which is of decimal, we just now converted it and we got the value of 0.24, and therefore the final answer becomes 447. So we take the integral part, the octal integral part 447, and 0.24 is the fractional part, and we write 24. So we have 447.24, and this point that we put here, it is similar to a decimal point, but only in this case, because we are in base 8 or in the octal base, we will call it as an octal point. So this becomes the method of conversion from decimal to octal.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
We now discuss the conversion of a binary number to its equivalent hexadecimal value. We again see here the table of hexadecimal, decimal and binary numbers. As we can see, any hexadecimal number can be represented in groups of 4 bits. Now, the process to convert a binary number to hexadecimal involves certain additional steps. We know that the maximum digit in hexadecimal is F, which is having the equivalent value of 1111. So, given a binary number, we start from the least significant bit and form groups of 4 bits at a time. So, the reason we form groups of 4 bits is because the largest symbol in hexadecimal F requires 4 bits. So we will form groups of 4 bits at a time and we'll replace them with the hexadecimal equivalent. Now, it may happen that we do not have a group of 4 bits. In that case, we append leading zeros to make a group of 4 bits. So before we do the conversion, the number of bits should be a multiple of 4. For example, supposing we are given the number 110011. This has only 6 bits. So we must append two leading zeros to give us the number 00. This becomes the two leading bits, 0 bits, followed by 110011. And it will also help us in writing down if we keep a space or a gap after every group of 4 bits. Now let us take this first example, how to convert the binary number 111110 to its hexadecimal equivalent. So we'll start from the least significant bit and make groups of 4 bits. So we have our original number 111110. We have kept a space here to help us identify the 4 bits. Now if the last group in this does not have 4 bits, so we have here only 2 bits in the last group, we'll put 2 zeros to the left, so we have the number 0011 1110. So these 2 bits that we see here are the 2 padded bits so as to form a group of 4 bits. Now we'll start from the right and replace each group of 4 bits with its hex equivalent. So we'll replace 1110 with its hex equivalent, then we'll replace 0011 with its hex equivalent. So we'll have 1110 is equivalent to the hexadecimal E. Similarly, 0011 is equivalent to the hexadecimal 3. And therefore, the given binary number 0011 1110 is equivalent to the hexadecimal 3E. Let us now consider another binary number which is a mixed number. So we have the binary number 111011.11. Now to convert this into hexadecimal equivalent, we'll first consider the integer part, find its hex equivalent, then we'll consider the fractional part 0.11 and convert it into its hex equivalent. So let us start with the integral part 111011. Now this can be written as 0011 1011. So again, if we start from the least significant bit, form groups of 4 bits. So you'll have 1 1 0 1. This group of 4 bits is 1011. We are left with now 1 1. So 1 1 and we pad 2 zeros to the extreme left. So this gives us a group of 4 bits and another 4 bits. And now we convert each group to its equivalent hex value. So this becomes 3 1 1 0 1. This becomes equivalent to B of hexadecimal, and therefore our integral part is 3B in hex. Now let us take up the fractional part 0.11. Again we'll consider 0.11 and we'll put 2 zeros at the end. These 2 zeros are put here so as to give us a group of 4 bits. Now we'll take this group of 4 bits and write its binary equivalent. So this 1100 is equivalent to C of hexadecimal, and therefore the binary number 0.11 of binary is 0.C of hexadecimal, and therefore our complete number 111011.11 can be written as 3b followed by the hexadecimal point and C. This becomes the number in hexadecimal.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
In this video's lecture, we'll discuss the conversion of a hexadecimal number to its binary equivalent. We are familiar with the table of hexadecimal, decimal and binary numbers. We know that hexadecimal numbers 0, 1, 2, 3 up to F can be represented in terms of 4-bit binary values. For example, the hexadecimal number 6 can be represented as 0110 in binary. The hexadecimal number F can be represented as 1111 in the binary number system. Let us take this first example to convert the hexadecimal 36C to its binary equivalent. Now the procedure for this conversion is as follows. Starting from the least significant digit. In this example, the least significant digit is C. We'll replace each hex digit with its 4-bit binary equivalent. So we have the hexadecimal digit C, then we write the next digit 6 and the most significant digit 3. So we replace each hexadecimal digit with its 4-bit binary equivalent. C can be represented as 1100. We know that the decimal value of C is 12 and the binary equivalent is 1100. 6 of hexadecimal is equivalent to 0110 in the binary, and this is also the decimal equivalent. 6 is also the decimal equivalent for this binary number. And coming to the most significant digit 3, this 3 can be represented as 0011, and therefore 36C of hexadecimal can be represented as 0011 0110 1100. This becomes the equivalent binary number. Let us take the hexadecimal number with a fractional part. Our hexadecimal number is 7F.CA5. Now, to convert this hexadecimal number, we will break it up into two parts. One is the integer part, that is the part before the point 7F, and the part after the point, that is CA5. So we start with the integral part. The integral part 7F. This 7F, again we take each hexadecimal digit and write it in terms of its 4-bit binary equivalent. So 7 becomes equivalent to 011 of binary. F is equivalent to 1111. This is again the decimal equivalent is 15. So this becomes the binary value of 7F. 01111111 in hexadecimal. Now let us move on to the fractional part, that is CA5. So we convert the fractional parts 0.CA5 to binary. So we'll start with the decimal point with the hexadecimal point, and C is converted into its binary equivalent 1100. Remember, C is equivalent to the decimal value 12. So this becomes 1100. A of hexadecimal corresponds to 10 of decimal, which is 1010 of the binary. 5 corresponds to 0101 of binary, and therefore our fractional number point CA5 can be written as 0.1100 1010 0101, and now we can combine these two parts, the integer and the fractional part, and therefore the hexadecimal 7f.ca5 is equivalent to, here are the bits 0 1 1 1, that is the one part, 1 1 1 1, that is the next part, then we have the decimal point, or in this case it is the hexadecimal point, followed by 1100, here it is 1100, followed by 1010, so 1010 and 0101. This becomes our equivalent number in the binary number system.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
Hello. In this lecture, we will discuss the conversion of a hexadecimal number to its octal equivalent. Now, before we actually start with an example, let us quickly recheck the table of hexadecimal, decimal and binary numbers. Here we have the table of hexadecimal and decimal numbers along with their binary equivalents. So for example, we have the hexadecimal number 0 with its decimal value equivalent to 0, and in terms of 4-bit we can write it as 0000 as a 4-bit binary, and like this we have it for hexadecimal 1 2 3 up to f. F, as we know, stands for the decimal number 15, which can be written in terms of 4 bits 1 1 1 1. So for representing the hexadecimal symbol f, we require 4 bits. But when it comes to octal numbers go from 0 to 7. So if we look at the last octal digit here, 7, this requires only 3 bits, and therefore every octal number can be represented in terms of 3 bits. So here is the important point in this table. A hexadecimal number can be represented using 4 bits, whereas an octal number can be represented using 3 bits. Now with this background, let us start with an example. In the first example, we are given a hexadecimal number CAB. This is in base 16 and we want to convert it into its octal equivalent. So the steps to this are as follows. In step 1, we will first convert the given hexadecimal number to its 4-bit binary equivalent. We saw in this table that every hexadecimal number can be expressed in terms of 4 bits, and this is the logic we apply here. So CAB can be written as C can be replaced with its equivalent binary value 1100. So we can refer to this table here. We have C as 1100. This is the equivalent binary value of C. A can be represented as 1010. Here we have the equivalent value for A. A can be represented as 1010, and B can be represented in 4-bit binary as 1011. Let us verify this part. B can be represented as 1011. So we have the hexadecimal number, and each digit of the hexadecimal number has been expressed in terms of the 4-bit binary equivalent. Now, in step 2, we start from the least significant bit. This is our least significant bit. And from here, we form groups of 3 bits as we move from the least significant bit to the most significant bit. So starting from the LSB, let us form the groups of 3 bits. So we have 110 followed by 101. This is as we are moving from the right to the left. Then we have the next 3 bits 101, sorry, that is 010. So you have 010, and the last three bits 011. These become the last three bits. So we take groups of three bits starting from the least significant bit and keep moving towards the left. Now we start from the least significant bit again in this step 2, and we'll replace each group of 3 bits with its equivalent octal digit. So for example, this group here, 1 1 1 1 1 and 0, this will be replaced by its equivalent value in octal. So we have here 6 0 1 0 can be replaced with its octal value 2, 1 0 1 its octal value is 5, and 0 1 1 can be replaced with its octal value 3, and therefore the given number CAB is equivalent to 6253 of octal. Let us take the second example where we are again given a hexadecimal number, but this time this number has a fractional part. So we have, before the decimal, we have the integer part 54. After the point, we have the fractional value FB32. Now to convert this, we will write our given decimal number as 54.FB32. Again, as in the previous case, we take each hex digit and express it in terms of its equivalent 4-bit binary. So the 5 can be written as 0101, 4 can be written as 0100, the point is kept as it is, F can be replaced with its binary equivalent 1111, B can be represented with its binary value 1011, 3 is 0011, and this digit 2 can be written as 0010. Again, we form groups of 3 bits starting from the decimal point, starting from the point. Now observe this. We start from the point. As far as the integer part is concerned, we will collect 3 bits at a time. So we'll have 0, 0, 1. This becomes our one group of 3 bits. Then we move forward. We have 0, 1, 0. This becomes our next group of 3 bits. And then observe this. We need 3 bits. So we pick up the bit 0. We pick up the bits 1, 0, and we don't have another bit here, so we pad it with a 0, with a leading 0. So we have the 3 bits 1 0 0 reading from right to left. And now each of these groups of 3 bits, we replace them with its octal equivalent. So this becomes 1 2 4. We have the point, and now here again we convert each of these bits into groups of 3. So now let us start from the point, and now we move from the point towards the right. So we'll have a group of 1 1 1. This is a group of 3 bits. Then we have 1 1 0. This group is 1 1 0. Then we have the next 3 bits 1 1 0. That is 1 1 0. The next 3 bits 0 1 1, and the last 3 bits 0 0 1 is this. This 0 we can discard because it is not significant here, and therefore this each group of 3 bits can be again written in terms of its equivalent octal value. So 111 becomes 7, then similarly we have 110 6, 6 for this, 011 becomes 3, and 001 becomes 1, and therefore the equivalent value can be written as 124. This is the part that appears before the decimal point, followed by 0.76631. So we have 0.76631. So this becomes the equivalent value in octal number system.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
Hi, welcome to this session on binary addition and subtraction using ones and twos complement methods. Now, before we start with binary addition, let us first get familiar with the basic terminology used in addition. When we add two numbers, we use three words to describe this addition process. So first is what is added, to what, and giving the result. What is the result? So in decimal number system, as an example, if I have a number 237, this is the number to which we are adding the number 418. So what is added is 418. It is called as the addend. To what it is added is called as the augend, and of course the result is the sum. In a similar way, we'll be using these three terms, augend, addend, and sum, in binary addition. Of course, there is one more term that we use, and that is carry. So we may have a situation where a addition process involves the carry. So for example, 7 and 8, when they are added, 15, so 1 is the carry. So we have one more term here, and this number here we know we can call it as a carry. So these are the four terms that we'll be using. So augend, addend, sum, and carry. So now let us see the rules for binary addition. We have the first column here, augend. We have the addend. This is the number which is added to the first number, the augend. We have the sum, carry, and result. So in the first row we have 0 plus 0. So our first number is the augend. The second number is the addend. This gives us the sum 0, and there is no carry, so the carry is 0 and the result is 0. So this is the result that is shown here in the last column. Then the next row is augend 0, addend 1, sum is 1. There is no carry again, and the result becomes 1. So the result is the sum. Augend 1, addend 0, sum is 1, carry is 0, and the result is again 1. Now let us check this. We have augend 1 in the last row. Addend is also 1. So what we are adding is 1. Now this 1 plus 1. Now for a moment, let us assume that these two numbers were in the decimal system. So 1 plus 1 would have given us 2. Now this 2 can be written in binary as 1 0. So in the binary system we have augend 1, addend 1. So the sum is 1 plus 1. 1 plus 1 gives us the sum of 0, and the carry is 1. So we have the sum 0, that is the sum 0. The carry is 1. This is our carry 1, and the net result is 1 0, which is the final result here. So this is the complete table for binary addition. Let us take the example of addition of two unsigned binary numbers 1101 and 1001. So the first number is 1101. Now this, if we calculate, it will have the equivalent decimal value. Let us do this calculation in a space here. 1101, we write the bit weights 1, then the next bit has a weight 2, 4, and 8. Since this bit is 0, we can strike off its corresponding weight, and therefore this number has the equivalent decimal value of 13. The next number that we have is 1001, and we know that this has an equivalent value of 9, and therefore we expect in decimal the answer to be 22. Let us verify the answer here. 1 plus 1. 1 plus 1 should give us a sum of 0. So we have 0 and a carry of 1. Now we have 1 plus 0, which is 1, plus 0 is 1. This is 1 plus 0, 1. This is 1 plus 1, so it is 0 with a carry of 1. Now let us take this result And in this 5-bit number, what is the value of this in decimal? Again, let us write the weights below each of the bits. This first bit has a weight of 1, 2, 4, 8 and 16. So since this bit is 0, we can strike off its weight and we are left with 16 plus 4, 20, 22, and this bit is also 0, so its weight also we can strike out. So this also becomes 22, and therefore we can say that 1101 plus 1001, it has the equivalent value 10110 in the binary system. This is how we can calculate the sum of two binary numbers. Let us take now different cases of binary addition. There are four possibilities. One where both numbers are positive, for example 23 plus 15. We are using decimal numbers as an example, but of course when we do this we will be using the equivalent binary values. We may have a situation where the larger number is positive, so 23 plus minus of 14. So this is basically an addition where the second number is a negative number. The smaller number is negative. The larger number is negative. This is the third case. So we have minus 23 plus 14. And the fourth case where both numbers are negative. So we have minus 23 added with minus 14. So let us take these cases one by one. So if both numbers are positive, let us take the equivalent example. We want to find the addition of 5 and 2, but of course we will be doing it with using the binary values. So the solution will be, we take the number 5, its binary equivalent we know is 0 1 0 1. We take 2, its binary equivalent we know is 0 0 1 0, and now we use our table to do this calculation. So this we know 5 plus 2 will be 7, and we add the corresponding bits here. So 1 plus 0 1, 0 plus 1 1, 1 plus 0 1, and 0 plus 0 is 0, and therefore we see that the result is 0 1 0 1 plus 0 0 1 0 is 0 3 times 1, and this binary value of course corresponds to the number 7 of decimal. So this is our final result here. Let us take now the next example where the larger number is positive. So we have a case where we have plus 5 and minus 2 being added together. So let us see. In this case, since one of the numbers is negative, we take the ones complement of the negative number. So, and then we add the two binary numbers, and the end around carry is added to the least significant bit. Let us take this with an example. Plus 5, it's a positive number. We convert it into its equivalent binary value 0 1 0 1. Minus 2, first we find the magnitude of this. So by ignoring the negative sign, we find the magnitude of this 2 in binary format. This is 0 0 1 0. But since this is a negative number, we take its ones complement, and so the ones complement of 0 0 1 0, and so the ones complement of 0 0 1 0 is just obtained by flipping the bits. So we have 1 1 0 1, and when we add this we get here plus 3. Now let us check the values here. 1 plus 1 is 0 with a carry of 1. This is 1 plus 0 is 1. Again plus 0, that will give us 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. Now this number that we have here, this is the end around carry. This we can call it as the end around carry, and this we can represent it as EAC. So this end around carry, we will now take this and add it to the least significant bit of the previous sum. So we have 0 plus 1 1, this is 1 0 0. So here we get the result 0011, and we can see that this 0011 of binary corresponds to 3 of decimal, and therefore this plus 5 minus 2 can be represented as 0011. In this example, let us consider the situation where again addition of two numbers is considered, but the larger number is negative. So we have minus 5 plus 2. So since the number is negative, we take its ones complement. So first take the number 5, ignore the minus sign, and write its magnitude. So the magnitude of 5 in binary is 0101. We take its magnitude, if we take its ones complement, this becomes 1010. This is just by flipping the bits. The next number is 2. Since it is a positive number, we keep it as it is. So this is 0010, and now we add the two values. So we have here 0 plus 0 is 0. Then we have 1 plus 1 is 0 with a carry of 1. This 1 plus 0 gives us 1. This 1 plus 0 gives us 1. Now we can observe that this number 1100 is certainly not equal to minus 3. The magnitude is certainly not equal to 3. In this case, what we do is, since there is no end around carry, what we do is we take the complement of this number. We will take the ones complement of this number. The ones complement of this will be 0011, and this number is in the ones complement form. So we get the final result as 011, which is minus 3 in magnitude. Let us consider now the fourth case where both the numbers that are being added are negative. So the numbers are minus 5 and minus 2. Now since both numbers are negative, we'll of course have to take the ones complement of both. So minus 5, again first consider the magnitude. Its binary equivalent is 0101. Since it is minus 5, take its ones complement by flipping the bits 1010. The next number is minus 2. Again, since it is a negative number, first we will consider the magnitude, and its magnitude is 0010, that is absolute value. And because it is a negative number, we take its ones complement. So this ones complement will become 1101. Now we add these numbers. So we know that minus 5 and minus 2 in decimal would have been minus 7. Now we add these two numbers here. So we have 0 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 1 plus 1 is 0 with a carry of 1. Now observe this. Since there is a carry, we take this carry and we add it to the least significant bit of the previous result. So we have 1 plus 1, 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. This 1 plus 1 is again 0 with a carry of 1, which we put it here. Now, this result that we have obtained is of course not our equal, it's not equal to 7. So what we do here now is we take this and 1000 and we take its ones complement. So we'll take the ones complement of this. The magnitude part will become 111, and this is equivalent to the decimal number 7. But since our bit here is 1, this will become a negative number, and therefore we have the equivalent value minus 7. And therefore when we add minus 5 and minus 2, we have our equivalent value as 111, and this 1, the most significant bit, is indicating that it's a negative number. Now let us study the rules of binary subtraction. When we subtract two numbers, we again use three words to describe this process of subtraction. First, what is subtracted, from what, giving what. And of course there will be always the situation where we have to borrow something from another place. So let us understand. In decimal system, we have 237 minus 124. So here the number that we want to subtract, what is subtracted, is called as the subtrahend. It is called as the subtrahend. So 124 becomes the subtrahend. And we are subtracting it from what? 237. So this number we call it as the minuend. And the result of this is the difference. So this becomes the difference. If at any point we have to borrow from the previous place, then we have a new term or another term which we can call it as a borrow term. So that is the value that we borrow from a higher position. Now let us create the rules for subtraction. Here are the rules: minuend, subtrahend, difference, and borrow. So 0 minus 0 gives us the difference 0, and there is no borrow. 0 minus 1. Now let us understand this. Our minuend is the first number. The subtrahend is the second number. When we do this, the result of this is a difference of 1. But we can observe that this 0 is smaller than 1. So we cannot subtract 1 from 0. That means we must borrow from a higher position. And therefore, we have 0 minus 1 gives us the difference 1. No doubt the difference is 1. But there is also a borrow of 1 because we can borrow 1 from the higher position. Let us look at the third possibility where the minuend is 1, the subtrahend is 0. When we carry out the subtraction, 1 is greater than 0 and we have the difference 1 and there is no borrow. And the fourth possibility is where minuend and subtrahend both are 1, so the difference is 0 and there is no borrow. And again the subtraction is carried out by subtracting bits from the least significant bit and then proceeding towards the left to the higher bits. We have the same table here again for reference, and let us take an example to subtract the binary number 1001 from 1101. Now observe this. The number that appears after the word from, this number, it appears after the word from. That means this number has to be subtracted from 1101, right? So we start by first writing 1101. This has an equivalent value of 13 in decimal. And what do we have to subtract? 1001. This has the equivalent value 9 in decimal. Now when we carry out this subtraction, let us see. 1 minus 1, 0. 0 minus 0 will give us 0. 1 minus 0 will give us 1. And 1 minus 1 will give us 0. Now before we proceed from here, let us observe. This 13 minus 9 will become 4 in decimal. And if you observe this number now, 0, 1, 0, 0, this also has the equivalent value 4 in decimal. So here is a number. If you put the bits below this, 1, 2, 4, 8, since this bit is 0, strike off the weight. These two bits are 0, so strike off their weights, and all that we are left with is 4 into 1, which is 4. So this is how we calculate the subtraction. Let us take the next example where we have to subtract the binary number 0110 from 1011. So here is our first number 1011. This has the equivalent value 11. What we have to subtract is 0110. This has the equivalent value 6 in decimal. And now start. It has the equivalent value 6 in decimal. So let us do this calculation. 1 minus 0 is 1. 1 minus 1 is 0. Now observe this. 0 minus 1. We cannot subtract 1 from 0. So what we do is we borrow 1 from the higher position. So this becomes 1 0. And now we have 1 0 minus 1. So we are doing 1 0 minus 1. Now, there's a simple way to understand and remember this. In binary, 1 0 is also equivalent to 2 of decimal. So essentially what we are doing here is, we are doing, after we borrow 1 from here, we are saying 1 0 minus 1. But 1 0 as as if 2 minus 1, which is 1, and therefore 1 0 minus 1 is 1. Now since we had a 1 here and that has been borrowed here, this becomes 0, and so 0 minus 0 is 0, and therefore you get the value 0 1 0 1 of binary, which is nothing but 5 of decimal, and that's what we were expecting here. 11 minus 6 is 5. So here the process of borrowing 1 from the higher place to carry out the subtraction, this is important. And as we said, this 1 0 minus 1 can be thought of as 1 0 can be thought of as 2, 2 minus 1 is 1, and that is why 1 0 minus 1 is equal to 1. Now let us study the subtraction of binary numbers using 2's complement. We have two numbers here. We have to subtract the binary number 1 0 1 0 from 1 1 0 0 using 2's complement. We can see that this number from which we have to do the subtraction is larger than the second number. So let us start. The first number is 1100. The second number that we have to subtract is 1010. Since this is the number to be subtracted, we take its 2's complement. Now we add these two because we have already taken the 2's complement. So this becomes 0110. Now let us take the addition of these. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0 with a carry of 1, and that 1 plus 1 gives us 0 with a carry of 1. Now observe this bit 1, which is shown in red. This bit we will discard. If we discard this bit, we are now left with a minus b is 0010, and we can see here the equivalent decimal 1010 in decimal would have been, again let us see the weights, 1 2 4 8. So this bit is 0, discard the 4, this bit is 0, discard the 1, so this would have been 10. The number that we have, this other number is 1100. This has the equivalent value 10, and when we subtract 10 from 12, we expect the answer to be 2, and that is what we get here in binary form. So this is nothing but 2 of binary. So the conclusion is this: if a is greater than or equal to b, a is the first number, the sum produces a carry. This is the carry that we have produced. The sum produces a carry. This carry should be discarded, and the result is a minus b. Let us take the next example where we have to again find a minus b using 2's complement subtraction. But now let us understand the change in this situation. A is 1010. This has the equivalent value in decimal 10. B is 1100. It has the equivalent value 12. So we are basically doing now 10 minus 12, which we know is going to be minus 2. So we start with our first number A1010. Since it is positive, we keep it as it is, 1010. B is 1100. This is our original number. We find its 2's complement. So the 2's complement will be 0100. We have already seen in an earlier session how to calculate the 2's complement, but the basic idea is very simple. To find the 2's complement, start from the least significant bit and keep on writing the bits as they are till you come across the first one bit. So we have 001, so we have 001, and after that just flip the bits as they come. So we have 1, it flips to 0. Now Let us add these two. The sum of these two becomes 1110. Now observe, we want the number -2. This -2 should at least we should have here 10 as our magnitude part. But what we have is 1110. So what we do in the next step is, there is no carry and therefore the number must be negative. So what we do here is, we take the 2's complement of the value of this sum. The 2's complement of this will be 0 1 0 0. So this is the 2's complement and it's a negative value, and therefore a minus b is -2. So our conclusion is, if a is less than b, the sum does not produce a carry. There is no carry. So we take the 2's complement. Here we have taken the 2's complement of the result. This is the 2's complement, and we place a negative sign. So this becomes our value 0 0 1 0. That becomes the equivalent magnitude 2 of decimal.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
Hi, welcome to this lecture, hexadecimal number to decimal number conversion in section 4. In this lecture, we will study how to convert hexadecimal numbers to their decimal equivalent. But before we do that, you may want to remember a few powers of 16 which will help you to do the calculations quickly. For example, we have 16 raised to 0 is 1, 16 raised to 1 is 16, 16 square is 256, etc. And even if you remember up to 16 raised to 4, that is 65536, this should help. In the similar way, we have the fractional values. 1 upon 16 is 0.0625, 1 upon 16 square is 0.0039, and 1 upon 16 cube is 0.000244. Let us take the first example of how to convert a hexadecimal number B41A to its decimal equivalent. Now, the first thing that we need to do is, we need to identify the least significant digit, which is A in this hexadecimal number, and the most significant digit, which is B. And before we start solving this, let us keep this table handy, which gives us the equivalence between hexadecimal numbers and decimal numbers. So we know that any symbols from 0 to 9 in hexadecimal have the equivalent value 0 to 9 in decimal, but symbol like A has a decimal value 10, B has an equivalent decimal value 11, and so on, and F has an equivalent decimal value 15. So we will use these equivalent values when we convert this number from hexadecimal to decimal. Now, in this given number, the least significant digit, that is A, has the weight 16 raised to 0. The next digit has the weight 16 raised to 1. What it means is, this A will be multiplied with the power 16 raised to 0. 1 will be multiplied with 16 raised to 1. Of course, when we say A will be replaced by its equivalent decimal value 10. And in a similar way, B will be replaced with its equivalent value 11, and that B will be multiplied with 16 raised to 3. So we say that B has the maximum weight here. Now we can write B41A of hexadecimal as equal to B into 16 cube plus 4 into 16 square plus 1 into 16 raised to 1 plus A into 16 raised to 0. So here is a simple way to remember. If we start writing from the least significant digit and move towards the most significant digit, observe A is multiplied with 16 raised to 0. Here 16, this is the radix of our number system that is given to us. This is the radix of the given number system. So starting from the least significant digit, Each digit, for example a, is multiplied with an appropriate power of the radix, and we start with the power as 0. So a into 16 raised to 0 plus the next digit is 1, so 1 into 16 raised to 1. And now as we move towards the most significant digit, we keep on multiplying by appropriate powers of 16. So the powers of 16 keep increasing as we go from the least significant digit. As we move towards the most significant digit, you will observe that the powers of 16 keep increasing. Power of 16 is 0, 1, 2, and 3. So this becomes the equivalent value. This can be written as, now using our table, we will substitute. So B, we know, has the equivalent value 11. So we have B replaced with the decimal value 11 into 16 cube. So that is 4096 plus 4 into 16 square is 256 plus 1 into 16 plus a into 16 raised to 0. Now a, we replace it with its equivalent decimal value, that is 10. So 10 into 16 raised to 0 is 1, and this can be simplified into 45,056 plus 1024 plus 16 and plus 10 into 1 is 10, that is equal to 46106 of decimal, and therefore the given hexadecimal number can be expressed as 46,106 of decimal. Let us take the second example where we convert a mixed hexadecimal number. So this number is CAB.13, and this has an integer part and also a decimal part or a fractional part. We want to convert this into the decimal equivalent. Now the way to do this will be, we first take the integer part and convert it into the decimal equivalent. Then we will take the fractional part and convert it into its decimal equivalent. And once we have the two parts in decimal, we'll just separate them with a decimal point. So let us start with the integer part, CAB. So we convert the integral part CAB to decimal. CAB can be written as C into 16 raised to 2 plus A into 16 raised to 1 plus B into 16 raised to 0. So remember, this B is the least significant digit, and as we move from the least significant digit towards the left, we keep on increasing the power of 16 by 1. So 16 raised to 0, 16 raised to 1, 16 square, and this can be written as, we substitute the equivalent decimal value for C, 12 into 16 square, plus this will become A is replaced by 10 into 16 plus B has the equivalent decimal value 11 into 16 raised to 0. So this can be written as 12 into 256 plus 10 into 16 plus 11 into 1. 16 raised to 0 is 1, and this has the equivalent value of 3243. Now let us come to the fractional part, which is 0.13. This is again in hexadecimal, so we will convert this into the decimal. Now 0.13 can be written as 1 upon 16 plus 3 upon 16 square. Now the logic for this is similar to what we do for decimal number system. So if we had a number in decimal system 0.13, supposing this was a number in decimal, then we know that this could have been written as 1 over 10, because 0.1 can be written as 1 over 10, plus 3 can be written as 3 upon 100, right? So this is the same logic we are using. So if this number 0.13 would have been in the decimal system, we would have divided each digit on the right of the decimal by appropriate power of the base being 10. In this case, the base is 16, so we take each digit 1 and we divide it by the power 16. Then the next digit 3 divided by 16 square, and this can be written as 0.0625, 1 upon 16 is 0.0625, plus 3 upon 16 square is 0.01172, and this, when we calculate, comes to 0.07422, and therefore the given hexadecimal number CAB.13 can be expressed as, so we take the integer part 3243, this is our integer part 3243, we separate it with a decimal point and followed by 0.07422, so we have 0.07422, and this becomes our decimal equivalent for CAB.13.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
Welcome back to this section. We now discuss the conversion of an octal number to its decimal equivalent. Let us take the example of converting the octal number 327 to its decimal value. We know that an octal number is also a positional number system, just like the decimal system, and therefore each position has a weight assigned to it. So if you look at the number 327 of octal, the digit 7 is the least significant digit and it has a certain weight assigned to it. The digit 3 in this example is the most significant digit and it will have the highest weight assigned to it. So the LSD in this example has the weight 8 raised to 0, the next digit has the weight 8 raised to 1, and the most significant digit has the weight 8 raised to 2. Now we have taken here 8 because the base of this number system is 8. So we can say that 327 of octal is equal to 3 into 8 raised to 2, because this digit 3 is in the position with most significant, is the most significant digit, and therefore we multiply this digit 3 with 8 raised to 2 plus 2 into 8 raised to 1 plus 7 into 8 raised to 0. So the easy way to do this will be to start with the base and keep on increasing the base power of the base from 0 to 1 to 2, and therefore 327 of octal is equal to 3 into 8 raised to 2 plus 2 into 8 raised to 1 plus 7 into 8 raised to 0. This can be written as 3 into 64 plus 2 into 8 plus 7 into 8 raised to 0 we know is 1, and this is equal to the value 215. This 215 is of course the value in the decimal system. Let us take the next example where we have a fractional number. So our octal number is 327.14 and we wish to convert it into its decimal value. So we'll first consider the integer part 327, and as we got in the earlier example, this 327 is 215 of decimal. Now let us take the fractional part 0.14. This 0.14 of octal can be written as, now observe this digit 1 appears in the first position after the octal point. So we write this as 1 divided by 8, or we can say 8 raised to 1. So because the base is 8, so this will be divided by 8. The next digit is 4, so we'll have plus 4 divided by 8 raised to 2. So this is the analogous to what would happen if you had a number like 0.14 in the decimal. Then 0.14 we would say is 1 divided by 10, because in decimal the base would have been 10. So in this case 0.1 is 1 divided by 8 and 0.04 is 4 divided by 8 raised to 2, and this if we calculate is 0.125 plus 0.0625, which is equal to 0.1875, and therefore the equivalent value is 215.1875. So we have taken the integral part 215, and then we have the fractional part 0.1875. Let us take one more example to observe a very important result. Let us consider the number 127 of octal. We will convert it into a decimal number. So now 127 of octal can be written as 7 into 8 raised to 0. So we start with the least significant digit. This digit will be multiplied with 8 raised to 0. 8 is the base of this number system. So 8 raised to 0 plus 2 into 8 raised to 1. So the next digit is 2. So 2 into 8 raised to 1. And observe, as we move from one digit to the next, as we move from the least significant digit to the most significant digit, the power of 8 or the power of the base keeps on increasing. And therefore, when we consider the most significant digit, we'll have 1 into 8 raised to 2. And this can be written as 1 into 64 plus 2 into 8 plus 7 into 1, which is 87. And therefore, 127 of octal is 87 of decimal. Now, here is the important result. When we convert from a lower base to a higher base, so we went from a lower base 8 to a higher base 10, the number of symbols used in the higher base we found is less. So when we were in base 8, we were using 3 symbols to represent this number. But when we went into a higher base, like base 10, we were using only 2 symbols. So when we convert from a lower base to a higher base, the number of symbols used in the higher base may be less. And vice versa, when we convert from a higher base to a lower base, then the number of symbols may be more. So if we go from 87 in base 10 to base 8, we will be using 3 symbols 1 to 7. So this is the second important result.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
In this lecture, we will see how to convert an octal number to its equivalent binary value. Now, in this first example, let us consider a number 263 which is in the octal, and we want to convert it into the equivalent binary value. Here we have shown the table of octal numbers and the equivalent binary values. So for example, the octal number 0 is represented by the binary 3-bit binary value 000. The octal number 3 is represented by its equivalent binary value 011, and like this, octal number 7 is represented by the equivalent binary value 111. Now let us start with the solution of this 263. How do we convert it into its binary equivalent? Now the procedure is this: we will take the original number and we'll replace each digit of this number. Each digit of this number will replace it with its 3-bit equivalent binary value. But we have to be careful that we should not ignore any zeros of the binary value. Even the leading zeros, like the 0 here, or in these example these zeros here, these zeros must be included. So for example 263, so we'll take the digit 2, so we'll write the number 263. So the binary equivalent of 2, we can refer to this table. So the equivalent of 2 is 010. So we have the binary equivalent 010. Then let us consider the octal number 6. This octal number 6 has an equivalent value of 110. So we have equivalent binary value 110, and the octal number 3 is replaced by, or it is represented by 011. So there we have 011, and therefore the octal number 263 can be represented as 010 110 and followed by 011. This becomes the equivalent binary value. Let us take the next example where we have a fractional value. So the octal number given to us is 43.0216. This is our original octal number and we want to find the binary value. Again, to convert this, we will first break up this number into two parts. We will start with the integer part. Now, the integer part is the part which appears before the octal point. Since this is an octal number, the point that appears here, we call it as an octal point. So this is what is the name for this point. This is the octal point. Now, we'll start with the number 43 of octal. We'll replace it with its equivalent binary value. So 4 is replaced by 100 because the equivalent value for 4 in binary is 100. 3 is replaced with 011. We have 3 replaced with 011, and therefore 43 of octal becomes equal to 100011 of binary. Now we'll take the fractional part, that is the part which appears after the octal point, that is 0.0216. Again, this number is given to us in the octal, and starting from the octal point onwards, we will take each octal digit and express it in the form of its 3-bit binary equivalent. So the 0 becomes 000, 2 is represented with the octal value 010, 1 we represent it with its equivalent binary value 001, and 6 we are representing it with its equivalent binary value 110. There we have 6 with its equivalent binary value of 110, and therefore the complete number 43.0216 of octal can be represented as, we take the integer part which is 100011. This is our integer part. This is followed by the binary point. Now this becomes a binary point because we have converted the number to its binary equivalent. So we will write this is a binary point in the binary equivalent, and this is followed by, the binary point is followed by the fractional part of the number which we have obtained in binary. So we have 000, that is the first part, then we have 010, 001 and 110. So this becomes the equivalent value of the given octal number in the binary system. Let us take one more example here to convert the octal number 362.254 to its binary equivalent. So we start with the given number 362.254. This is our original number which is in octal, and now the process is simple. We take each digit of the octal and represent it with its equivalent binary value. So 3 of octal, we are replacing it with the equivalent binary 011, and we have to be careful, although this is a leading 0, all the zeros of the binary equivalent must be represented in the conversion process. So 3 is represented by 011, 6 of octal is represented with 110. There we have 6 of octal, we represent it with 110, and 2 of octal we represent it with 010. So we have 2 of octal is replaced with 010. Now this becomes the integer part of our original number. Now let us take the fractional part, that is the part appearing after the octal point. So the part appearing after the octal point is 0.254, and again we put the octal point as it is. 2 is converted into its equivalent binary value. So 2 has the equivalent binary value 010, so we represent that 010. Let us consider the next octal digit 5. Octal digit 5 is replaced with its equivalent 101, so 5 is replaced with 101, and the octal digit 4 is now replaced with the equivalent binary value 100. So we have the integer part, this is the integer part, we have the part that appears after the octal point, We have converted that into its equivalent binary value, and therefore our final value, the total value, will be equal to 362 has the equivalent value 011 110 010. Then we have this becomes our, now because it is in the binary system, we will call this as the binary point. So we have the binary point followed by 0 1 0 101 and 100. So this becomes the final value in binary system.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
In this video lecture, we will study how to convert an octal number to its equivalent hexadecimal value. Here is a table of hexadecimal, decimal and binary numbers, and we have also shown the octal numbers and their binary equivalent. So as we can see, hexadecimals 0, 1, 2, 3 and up to F, they can be represented by the binary values in terms of 4 bits. So 0 is 000, 1 is 001, etc. And F, which is the decimal value 15, can be expressed in 4 bits 1111. But when it comes to octal numbers, the octal numbers from 0 to 7, they can be expressed using just 3 bits of the binary, and therefore 0 is 000, 1 001, etc. And the largest symbol here, 7, can be expressed in the binary 111. So we will use this fact that octal numbers can be expressed in 3 bits, whereas hexadecimal numbers require 4 bits. Let us take an example of how to convert the octal number 637 to its hexadecimal equivalent value. So the procedure will be as follows. Starting from the least significant digit, here is our octal number 637. Starting from the least significant digit, we will convert each octal digit to its 3-bit binary equivalent. So if we start with the least significant digit 7, so we'll convert each of these digits 7 into its equivalent 3-bit binary value. So we saw in the earlier table that 7 can be expressed as 111, 3 can be expressed as 011, and 6 can be written as 110 in terms of binary. So this is our first step. Now in step 2, starting from the least significant bit, we'll form group of 4 bits as we obtained in the previous step. So starting from the least significant bit, we'll make a group 1 1 1 1. This becomes our first group of 4 bits. Thereafter we'll have 1 0 0 1. So we'll have 1 0 0 1. This becomes our next group, and now we are left with only one bit here, that is 1. So we write that bit. But since we want to have a group of 4 bits, we will pad this number with 3 leading zeros. Of course, we know that these 3 leading zeros will not change the value of the number. Now, we will take in step 3, starting from the least significant bit, again we'll replace each group of 4 bits with its equivalent hexadecimal digit. So let us start 0001. This is our first group of 4 bits. 1001, this is our next group of 4 bits, and 1111, which is the last group. So we'll start and convert each of these into its equivalent hexadecimal value. We saw in that first table that every group of 4 bits can be expressed in hexadecimal. So this becomes our least significant bit, and this 0001 equivalent hexadecimal value is 1. 1001 equivalent hexadecimal value is 9. 111F, this in decimal is 15, which is represented by the symbol F in hexadecimal, and therefore our number 637 of octal is represented as 19F in hexadecimal. So the symbol, the subscript H here indicates that it's a number in the hexadecimal system. Now let us convert another number which has an integer part and a fractional part. This is a number in the octal system and we'll convert it into hexadecimal equivalent. Now our solution is on similar lines. So our given number is 2727.413. We will take each digit here and write it in terms of its 3-bit binary equivalent. So the 3-bit binary equivalent becomes 010 for the 2. 7 of octal can be represented as 111 of the binary. We have the octal point. Because this number is in the octal system, we will refer to this as an octal point. 4 of octal becomes 100, 1 is 001 and 3 is 011. So our given octal number in binary is having the value 010111. Then we have the octal point 100, 100. Then we have 001 and 011. This becomes our number in binary. Now to convert this into hexadecimal, we'll form groups of 4 bits. Now the logic here is as follows. We start from the octal point, and as we start from the octal point, we'll first cover digits to the left. So I'll take a group of 4 bits at a time. So our first 4 bits are 1 1 1 0. These are the 4 bits we have taken, these 4 bits. Then we are left with 1 and 0. So we have 1 and 0. Now you will observe that we are having only 2 bits from this number, but we need a group of 4 bits. So we'll pad this with 2 leading zeros. So this becomes the equivalent value 0001. Its equivalent in hexadecimal is 1. This group of 4 bits 0111, it has a hexadecimal value 7. Here is our octal point, and now observe how we convert the fractional part. Again, starting from the octal point, we will move to the right, and we can observe that we'll take again 4 bits at a time. So we'll have 1000. So this is our first group of 4 bits. Thereafter we have 0101. So we have 0101. This is our next group of 4 bits, and now we are left with only one symbol, only one bit, that is 1. But since we need a group of 4 bits, we'll pad it with 3 zeros on the right. Now we know that in a decimal number, in a fractional number, any zeros padded at the extreme right do not change its value. So this part after the octal point 1000, its equivalent hexadecimal value is 8. 0101, its equivalent hexadecimal value is 5. 1000 has the equivalent hexadecimal value 8, and therefore our number 2727.413 of octal is equivalent to 17.858 of the hexadecimal system.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
In this video lecture, we will be studying about the logical operations. Let us first understand what are logical operations. We know that a byte is composed of 8 bits. In a computer, a word can be made up of multiple bytes. So for example, a word may be 2 bytes, 4 bytes, or 8 bytes, or as in many modern computers, a word may be made up of 16 bytes. Now, most algorithms can operate on the whole word. That means they can operate on either 4 bytes or 8 bytes or 16 bytes. But there are occasions when an algorithm has to operate on the individual bits or on a group of bits. So it may be that in some case a particular bit has to be changed from a 0 to 1 or vice versa. In such cases, we use what are called as logical operations. Now, logical operations are used to operate on bits, and they can be used to change the individual bit values. And that is why we say that logical operations are also called as bit manipulation operations or bitwise operations. Most programming languages like C, C++, Java, C Sharp, Python, and many others, they support logical operations, bit manipulation operations, or the bitwise operations. Let us see which are the logical operations we'll study in this lecture. The first is a left logical shift operation, which shifts bits to the left in a binary number. The right logical shift operation can shift the bits to the right. The third unusual type of operation is a right arithmetic shift operation. We'll see that this operation is needed to shift bits to the right, especially when we are dealing with negative numbers. Let us start with the first example of a left logical shift operation. We are given here a number 23, which is in the decimal system, and we have converted this into its binary equivalent, which is 10111. We will see step by step how to carry out the left logical shift by one bit. So we'll shift the bits of this number by applying the left logical shift operation, and we'll shift it by one bit. Now here is our original number A. We have shown the bits in separate boxes here. So our original number is 10111. So if we start from the least significant bit, this is our LSB, and if we start from the least significant bit and move from right to left, our bits are 11101. So here are the bits 11101, and since we want to make it a group of 8 bits, we have padded this number with 3 leading zeros. We know that putting leading zeros does not change the value of the number. Now let us shift these bits to the left by 1 bit. Now the way it will work is this. Starting with the least significant bit, we copy the least significant bit into the next higher position because we are shifting the bits to the left. Then we take the next bit and we shift it. So this one bit, the least significant bit, comes into a higher position. The next bit comes into the next higher position, so shift it to the left. Originally this bit, we can see that this bit was initially in a position where the weight is 1. This bit was in a position where the weight was 2. This was in the position with weight 4, weight 8, weight 16, etc. So the bit which is in the weight 2 position, it has been shifted into the higher position, shifted to the left by 1 bit. Similarly, this bit is shifted to the left by 1 position. So we just copy this bit here. This bit 0 is shifted to the left by again 1 position. This bit is shifted to the left by 1 position. Similarly, the bit 0 shifted to the left by 1 position. This is our bit 0, and this bit 0 is again shifted to the left by 1 position. Now observe what happens to this. This bit 0, which is the most significant bit in our original number, this bit is 0. There is no position where this can shift, and therefore this bit simply falls off, or we say that this bit is discarded. So it is no longer used here. Okay, number, the least significant bit is vacant, so we put a 0 in this least significant bit. Now it is very important to understand that this 0 that we have put here is not brought from the most significant bit. So we have not brought this 0 into the least significant bit. No, this 0 has been lost, it has discarded, and we have put a 0 in the least significant bit. Now if we look at this number, let us calculate what is the decimal value of this. This is in the position weight 1. The weight of this bit is 2, 4, 8, 16, 32, 64 and 128. Since the bits here are 0, we ignore these values. So the bit value here is 1, so 32. This is 0 bit, so we again ignore 16 here. We have bit 1 here, so 8. So 32 plus 8 is 40. 40 plus this 4, 44 plus 2, 46. Again this bit is 0, so we strike off this way. So the new number that we get here, the decimal equivalent of this is 46. So you can observe that the original number was 23. When we shift to the left by 1 bit, we get the new number 46, and this we can see is 23 2 times. That means the original number 23 has been as if multiplied by 2. So a left shift by 1 bit is equivalent to a multiplication by 2. Let us take the next example where we carry out the left shift by 2 bits. So we have the same number 000101111. We know its decimal value is 23. Now we will shift this by 2 bits. So here is our least significant bit. This least significant bit, we will shift it by 2 positions to the left. It comes here. The next bit will come here. So this was my least significant bit coming into this position. This bit is transferred to the next position, 2 bits to the left. Now we are on this one. We shift it to this higher position. The 0 bit is shifted to this position, 2 bits to the left. 1 bit is shifted here, and this 0 bit is shifted to this position. Now observe that this 0 and the 0 which is at the most significant bit, both these are lost. They as if fall off or they are discarded, and we ignore these. And now what happens in the positions at the extreme right? Both these positions which remain vacant will now be filled up with 0. Let us consider this number. What is the value? The weight of this bit is 1, weight of this bit is 2, this bit 4, 8, 16, 32, 64 and 128. So since the bit here is 0, we strike off, we don't use this. 64 and 1, so this is 64 into 1, that is 64. Similarly, this 32 value we strike off because the bit value is 0. Then we have 16, 1, 8 multiplied with 1, 4 multiplied with 1, and this 2, since the bit value is 0, this will become 0. 1 into 0, 0. And so what are we left with? We are left with 64 plus 16, that is 80, 88, 88 and 4 is 92. So this value that we get is 92. Now if you observe this, this is equivalent to multiplying the original number 23 with 4. 4 3 times is 12, 2 with a carry of 1, 4 2 is 8 and 1 9. So here is our conclusion. A left logical shift by 1 bit, this is what we did in our example 1. A left logical shift by 1 bit is equivalent to, we can say it is equivalent to a multiplication by 2. A left logical shift by 2 bits. Now we are shifting this to the left by 2 bits. It is equivalent to, we saw, this is equivalent to a multiplication by 4. But this 4 can be written as 2 raised to 2. So 2 raised to 2, and this 2 here represents the number of places shifted. So the number of places by which the bits were shifted. And therefore, in general, a left logical shift by n bits is equivalent to a multiplication by 2 raised to n. This is multiplication by 2 raised to n. So a left logical shift operation is basically a multiplication by 2 operation for every bit that we shift to the left. Let us now see the right logical shift operation. We consider our original number to be 20, and this number 20 of decimal can be written as 10100. We have represented this number 10100 in 8 bits. So let us start. Here is the least significant bit. If we start writing 001, so you have the least significant bit 001 followed by 01. So we have 001 followed by 01, and since these 3 bit positions are not given in our original number, we pad them with zeros. Now let us carry out the right logical shift by 1 bit. Now observe, if I have to shift these bits to the right, I will start with the most significant bit. We'll start with the most significant bit. So the bit which is at the extreme left or the most significant bit will be shifted by 1 place to the right. So this bit will become now 0. So we have shifted this bit. The next bit is shifted again by 1 place to the right. This becomes 0. This 0 is transferred to this bit position. 1 is transferred by 1 place to the right. 0 we again transfer by 1 place to the right. 1 is shifted to the right by 1 place. This 0 comes here, and now observe this. This 0 which is at the extreme right or the least significant bit, this falls off or it is discarded. This is discarded, and so we cannot account for this now, and the most significant bit is filled with 0. So again we must remember, it is not that this 0 is put into the most significant bit. No, this 0 falls off, and what do we put here? We put a 0 in the most significant bit. Now if we calculate what is the value of this in decimal, let us see. The decimal value of this position is 1, the weight of this is 2, 4, 8, 16, 32, 64, and 128. So again, all positions where the bit value is 0, we strike off those values, and we are left with 8. Again, this is bit 0, so we discard it. 8 and 2, 10, and this is again discarded. So this new number that we got is having the decimal equivalent value of 10, and we can see this 20 divided by 2 is 10. So a right logical shift by 1 bit results in a division by 2, and therefore we have this final value here 10. Now let us carry out the right logical shift by 2 bits. So again our original number is the same. We will start with the most significant bit and we will shift it by 2 places. So its original place would have been this. This would have shifted it by 1 place to the right. So we shift this by 2 places to the right. So the 0 comes here. This 0 appears in the next position. This 0 appears in this position. The 1 appears here. This 0 appears here. 1 appears in the least significant bit, and now observe this 0 and this 0, both these zeros, they will fall off and they will be discarded, and the positions which are now unfilled at the extreme left, these positions will be both filled with 0. And now let us consider what is the decimal equivalent of this. So here is the bit value 1, this is the bit value 2, this is the bit value 4, and since all these bits are 0, we can ignore writing the bit values. And now what happens? Since this bit value is 0, we can strike off this, and now the decimal equivalent is 4 plus 1, 5. And you can see this This 20 divided by 4 gives us 5. So here is our conclusion. A right logical shift by one bit is equivalent to a division by 2. A right logical shift by 2 bits is equivalent to a division by 4. But that can be written as 4 can be written as 2 raised to 2. So this 2 is the number of shifts, number of positions by which we shifted. And in general, a right logical shift by n bits will be equivalent to a division by 2 raised to n. So these become the important conclusions from this example. Now let us consider a very interesting example where we have to shift the bits of a number which is negative. So we are given a number -6 in the decimal system. This number we know can be expressed in 2's complement as 1010. This is in the 2's complement. This 1 bit here indicates to us that this number is a negative number. Now observe the important change that comes in this example. We are now carrying out a right shift operation, but this is called as a right arithmetic shift. Now what is different in this? Let us understand. We'll shift one bit to the right, and the way it will start is this. We will take the bit 1. This bit will be shifted to the right by one position. This bit is shifted to the right by one position. This bit is shifted to the right by one position. This bit, which is the least significant bit in our original number, it is lost. But observe this part. Since our original bit 1 in the most significant bit position, this 1 was used to indicate the sign of the number. That means this indicates that our original number is negative. So we cannot afford to lose this bit, and so what we do is, to preserve this bit, to preserve the significance of this, we copy this one value in the most significant position. So in my part, in the B value, we have most significant bit is still 1. So the bits are shifted by one position to the right, but the most significant bit is copied into the MSB part of the new number, and the least significant bit is lost. So this becomes our new number. Now if you calculate this, you will realize that this number is nothing but the 2's representation of the number -3. So this is the representation of -3 in 2's complement, and which tallies with our calculation. If when you divide -6 by 2, of course we expect the result to be -3, and that's what we'll get. The only thing is that this number that is given to us is in the 2's complement. So why do we need a right arithmetic shift? So if you observe, this shift was similar to the right shift, the right logical shift. The only difference that came up was this most significant bit, which is 1, is copied into the result. So why do we need a right arithmetic shift? The right arithmetic shift is used to divide negative integers. We have to divide negative integers when the most significant bit is the sign bit. We know in the 1's complement, this bit is the sign bit. Okay. Now what can be the simple summary of this? A right arithmetic shift of one position moves each bit to the right by 1. The least significant bit is discarded. We saw that the least significant bit is lost, it is discarded, and the vacant most significant bit, this was our original vacant most significant bit, it is filled with the value of the previous MSB. So this one MSB is copied into the new number. So this preserves the sign, and we have also been able to achieve the division. Let us now consider the shift operations on fixed size numbers. We know that a computer can represent numbers in fixed sizes. So as we said earlier that a word is made up of 2-bit bytes or 4 bytes or 8 bytes or 16 bytes, and therefore the number of bits that can be represented is fixed. If in carrying out a shift operation, for example in carrying out a left shift operation, certain number of digits or certain number of bits are added to the right, then certain number of bits must also be discarded at the left, because ultimately we have a fixed number of bits in a word, right? So let us take as an example an unsigned number, and our number is 0000 and 1110. We can shift this number to the left by one place. So let us write our original number 0000, then we have 1110, and in decimal this number is of course 14. This is the least significant bit of the number and the most significant bit. Now let us see what will be the result when the number is shifted to the left by one bit. So this 0 occupies this position, the 1 here occupies this position, this 1 occupies the next higher position, this one occupies the next higher position, the 0 here comes into the next higher position, this 0 will be brought here, this 0 occupies the most significant bit of the new number, and this most significant bit is lost, it is dropped off, and therefore this position that we have is now filled up with a 0. Now let us check what is the decimal value of this. This is 1, the weight of this is 2, 4, 8, 16, and since these bits are 0 we need not write the weights here, but if we had to this would be 32, 64, 128, but since the bits are 0 we can strike off these values, and therefore the number that we get is 16 plus 8 24 plus 4 28. Again these two bits can be removed, and therefore the number that we get is 28 of decimal. This is of course consistent with what we said earlier, that a left shift by 1 is equivalent to a multiplication by 2. But let us consider an example of another unsigned number. Okay, now in the previous example, of course, this bit MSB 0 that was there, this was a 0 bit. It was not a significant 0 because it was at the extreme left, and therefore there was no change in the result. Our results are consistent, right? But let us consider an 8-bit number. This number is 10100101. We shift this number to the left by one place. So let us write our original number 10100101. This negative number is minus 37. It is in the 2's complement. This 1 in the most significant bit tells us that this is in the 1's complement. Let us now carry out a shift operation, a left shift by 1. So we can see a left shift by 1 will bring this bit to the higher position. The 0 comes into this position, 1 comes into this 0 occupies the next higher position, this 0 is in the next higher position, 1 shifted here, the 0 is shifted here, but now observe something very interesting. This bit 1 is lost because there is no position to the left, so this bit is lost. But remember, this was supposed to have been the sign bit, and we have of course put a 0 in the least significant bit position of our new number. So if you look at this result, we find that a 1 which was an indicator of a negative number that has been lost, and this number that we get now is become a positive number. So this is of course a loss of data which is undesirable. Now let us summarize these rules of left shift and right shift operations. A left logical shift by one position will shift the bit to the left by 1. The most significant bit is lost and the least significant bit is filled with 0. This is what we saw in the first example in this video session. A right logical shift by one position will move each bit to the right by one. Now, since we are moving to the right by one, the least significant bit will be pushed away or it will be lost, and the vacant most significant bit will be filled with a 0. A left arithmetic shift. This is identical to a normal left logical. So a left arithmetic shift of one position will move each bit to the left by 1. So the least significant bit will be again filled with 0 and the most significant bit is discarded, and this is identical to the left logical shift. But let us check what happens to the right arithmetic shift. We saw in the earlier example that a right arithmetic shift will move each bit to the right by 1. The least significant bit will be of course pushed away, so it is discarded. But the most significant bit, because it contains the digit 1 or it may contain a digit 0, and these bits are important. So the most significant bit of the new number is filled with the value of the previous most significant bit. This is the important difference between a right arithmetic shift and a right logical shift. Arithmetic shift operations are used for carrying out division or multiplication of an integer variable. A left shift is equivalent to a multiplication by 2 raised to n, and n is the number of shifted bit positions. So if you were to shift to the left by 2 bits, it would be equivalent to multiplication by 2 raised to 2, that is 4. The result of a right shift operation, on the other hand, is a division by 2 raised to n. So n is again the number of bits through which we shift the values. And this is an important one. If the leftmost digit is significant, for example, in a negative number in the 2's complement representation, if the leftmost digit is significant, shifting the left no longer multiplies by the base b. So the base b is of course 2 in the binary system. So if the leftmost digit is 1 and if we shift to the left, this leftmost digit will be pushed off on the left and it will be lost. So shifting left does not imply multiplication by 2 in all cases. These are the important rules that we must remember when carrying out left and right shift operations.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
Welcome to another video lecture in section 5. In this video lecture, we'll study about the concept of sign extension. What is sign extension? Sign extension is the process of converting a number with a given number of bits to a number with a larger number of bits. So for example, supposing we have a binary number given to us which is 1101, 0101. This we can convert it into a 16-bit number. So we start by first writing down the bits from the least significant bit and we pad up the remaining 8 bits with zeros. So our original 8 bits are shown here and the remaining 8 bits on the left become the padded bits which are 0. Now, sign extension is needed when we are to carry out the addition of two binary numbers with different number of bits. So for example, if we have an 8-bit number and a 32-bit number, if we get the correct result, we must convert the 8-bit number to 32-bit number, and this process is called as sign extension. As an example, let us take two numbers. The number given to us 8, this is of course a number in the decimal system, and its equivalent in binary is 1000. Another number given to us is 9 in the decimal system and its binary equivalent is this. When we carry out the addition of these two numbers, the result we get is 10001. This is of course in binary again. So we can see that the two original numbers, binary numbers, were having 4 bits each, but the result is made up of 5 bits. So when we add two binary numbers, the result may extend by 1 bit, and the resultant binary number may need one more bit if there is a carry. So this one is the carry in our addition. To represent such a result in the correct form, we must allocate an additional bit for representing the magnitude of the numbers. What it means is, if my two numbers were of 4 bits each, the addition of these, the final result cannot be accommodated in 4 bits, and so we must do an sign extension, or we must extend the number of bits. As a first example, let us see the sign extension of an unsigned number. So what is the 16-bit representation of the 8-bit unsigned number? Now we are told that this number given to us is an unsigned number. So here is the number 10110010. So all the bits contribute towards the magnitude. We have written the original number given to us here. This is the least significant bit. Now, the process of this conversion is very simple. Since this is an unsigned number, we will just copy down all the bits starting from the LSB into each position in the 16-bit number. So we copy these bits, and now the remaining 8 bits will be all filled up with zeros. So we fill up these bits with 0 because our number is an unsigned number. In this example, let us understand how we do the sign extension of a signed magnitude number. So let us start with the example. We are given here a number 100000111. This number is in the sign magnitude representation. So the bit in the most significant position, MSB, this bit represents the sign of the number, and the remaining bits contribute towards the magnitude. So we wish to find what is the sign extension value of this number. So we first copy down this number in the 8-bit position, and this is our least significant bit. Now the method to do this will be, we first move the sign bit of the 8-bit number. This is the MSB of your original number. It is also the sign bit. So we move this sign bit to the sign bit of the 16-bit number. So this is my 16-bit number, and this 16-bit number will have the MSB as the sign bit. So we move the MSB of the 8-bit number to the MSB of the 16-bit number, right? Okay. Thereafter, we will copy the remaining 7 bits of the original number starting from the LSB. So we copy the remaining 7 bits, and now last bit 1 has already been copied into the most significant bit of the 16-bit number. So we do not copy this bit into our new number, rather we put a 0 in the new number, and all the remaining bit positions will now be marked with a 0. So that becomes the sign magnitude representation of 16 bits, right? Okay. In this example, let us consider the sign extension of 2's complement number. Now, to convert a 8-bit 2's complement number to a 16-bit number requires again 2 steps. Let us consider the original number given to us, that is 11101110. This is already given to us in the 2's complement representation. We write down our original number here. This is the most significant bit, and we have here the least significant bit. Now, to convert this into a 16-bit equivalent number, the procedure is as follows. We will first copy down the 7 bits starting from the least significant bit. So here are our 7 bits. We copy down these 7 bits into the respective positions in the 16-bit number, and now observe this. This most significant bit in the 8-bit representation, this is our most significant bit. This high bit, we will copy it to each of the remaining positions in our new number. So this bit, the high bit, will be copied into each of the positions which are now vacant in the 16-bit number. So we'll have all these positions being filled up with 1.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
Welcome to this session on BCD or 8421 code. What is the BCD code? The term BCD stands for binary coded decimal. In this system, each decimal digit of a decimal number is expressed in terms of its 4-bit binary equivalent value. So, to write a decimal number in BCD form, we don't convert the entire number to binary. So, a BCD code is not a pure binary form. Instead, what we do is we take each digit of the decimal and we will write it in terms of its 4-bit binary value. We'll see this with the help of some examples. Now, one problem that is observed is that a BCD code becomes simpler to write from the decimal value because it does not involve the complications of divisions which are necessary when we convert a decimal to pure binary. But a BCD code has a disadvantage in that it requires more bits than a pure binary code. Now, this code is also called as the 8421 code because of the bit weights. The positions have weights 1, 2, 4 and 8 starting from the least significant bits. So these are the 4 weights of the 4 bits of the BCD code. Now, BCD code is a weighted code because each position represents a specific weight. We already said that these are the weights. So we have the weight 1, then we have the weight 2 for the next bit after the LSB, then the weight 4, and the most significant bit will carry the weight 8. So it is a weighted code. Let us take this first example where we have to calculate the BCD equivalent of the decimal number 743. So this is the number in decimal system. Now we'll start by first writing the digits of our original number 743. So 743 become the digits. Now each digit will be converted into its equivalent BCD code. So 7 is 0, 1, 1. Now this is easy because we just need to remember that each bit here carries a weight. So if I start from the least significant bit, this carries the weight of 1, this has a weight of 2, this has a weight of 4, this has a weight of 8. And wherever we do not have a bit, that value is cancelled, and therefore we can see that this is 4 plus 2 plus 1, 7. Here is the next number 4. Again, if we remember that we need 4 bits, and these 4 bits will have the values or the weights 1, 2, 4 and 8. Since we want the decimal number 4, the only bit that can be set or the only bit that can be on is the bit corresponding to this position, and therefore the code becomes 0100. Similarly, for decimal number 3, the equivalent BCD code is 0011, and therefore we have the equivalent BCD code is 0111, 0100 and 0011. This is our equivalent BCD code, and to signify that this is a BCD code, we put the subscript here, and that subscript we write it as BCD. Now let us consider the second example where we have to find the BCD equivalent of the decimal number 29.85. Now again we will write the digits of this number separately, 2985. We are for the time being ignoring the decimal point, and we will take care of that towards the end of this problem. Now the equivalent BCD value of each of these digits. So the decimal number 2 has the BCD code 0010. Again we can see that this corresponds to the weights 1, the weight of this is 2, 4, 8. Since we want the number 2, we have this bit is set or it is 1, and all the other bits will be 0. So this becomes BCD code for 2. We have the BCD code for 9, 1001, 8 is 1000, and 5 is 0101. So this becomes the BCD code for 29.85, and we can express it as this is the BCD code. So we have the first part 0010, then we have 1001, and now here we take care of the decimal point, so we put the point here, then again 8, so we have 1000. 5 can be written as 0101, and we put a subscript here BCD to indicate that this is the number in the BCD system. Now here is an important point to note about the BCD code. We can observe that for each of these the BCD codes are given. So we have 0, the BCD code is given here, 1 is 0001, 2 is 0010, but one thing that we'll observe is that the decimal digits go only from 0 to 9. 10 is not a decimal digit. 10 is a decimal number which is made up of 2 digits. Similarly, 11, 12, 13, 14, 15, these are not digits by themselves. They are numbers made up of 2 digits. So we'll observe that once we have reached the digit 9, the BCD code is 1001. But when we have 4 bits, then we can always have another pattern of 4 bits, which is 1010. Now this corresponds to the binary value. This corresponds to the decimal value 10. Similarly, we have 1011. This corresponds to the decimal value 11. This is corresponding to 12, and so on. And we have 1111 corresponding to 15. But these binary codes are never used in the BCD code system. The reason is that the maximum digit that we have is 9 in the decimal system, and therefore these codes are called as forbidden codes, or they are also called as invalid states, and this group is called as a forbidden group or the invalid group. Let us take the third example, and in this we will carry out the conversion of a BCD number to its decimal equivalent. So we want to find what is the decimal equivalent for 1001001. Now we start from the least significant bit, and we will make groups of 4 bits each. So we'll start from the least significant bit. We'll have 1 0 0 1. So here is our starting from LSB, and as we move towards the left, then we have 0 1 0 0. So we have the next group 0 1 0 0, and now observe this. We need 4 bits, but we are left with just 1 bit. So we write that 1 bit, and then we pad 3 bits which are shown here 0 0. These are the 3 bits, so as to make up a group of 4 bits. Once we have this, then in step 2 we will write the decimal value of each group of 4 bits. So the decimal value of this will be 1, the decimal value of 0010 will be 2, and the decimal value of this will be 9, and therefore our given BCD number, this our given BCD number can be written as 129 of decimal system.
This live stream is a collection of helpful videos on my channel. If you find yourself wanting to check out the original video, there is a link in the description which will take you there and have all of the original links that were included in the video. Please subscribe to the channel and share the link with your friends and colleagues. Thank you.
Welcome to this section on complements of a number system. Let us first understand what is meant by complement of a number system. All digital systems use complement of a number to simplify the subtraction of numbers. So, for supposing we have a number which is in base r. Now this may be a binary system with r equal to 2, or we could have a decimal system where the base or radix is 10, or in a hexadecimal system where the radix r is 16. Now in each of these number systems there are 2 complements associated, and these 2 complements are called as the r's complement. That means that is the complement of the same value as the number system. So for example, in a binary system r is 2, so we'll have r's complement as 2's complement, and the second complement is called as the r minus 1's complement. So in a binary system with r equal to 2, we'll have 2 minus 1, that is 1's complement. So we'll have the 2's complement and the 1's complement. Now the r's complement is called as the radix complement because r corresponds to the radix, and the r minus 1's complement is called as the diminished radix complement. Now, for a binary number system, as we said, r is 2, so the complements will be 2's complement and 1's complement. This we saw is because we have the r's complement and we also have the r minus 1's complement. So with r equal to 2, we'll have the 2's and 1's complement. In a similar way, for decimal system, r is 10, and therefore the two complements will be the 10's complement, which is r's complement, and the 9's complement. For octal number system, r equal to 8, we'll have the 8's complement and the 7's complement. And for hexadecimal, of course, we'll have the 16's and the 15's complement. So these are the most commonly used number systems in computer science, and we have discussed what are the two complements in each of these systems. Now let us start by first understanding how do we obtain the r's complement of an n-digit number. So let us consider a number. This is a 4-digit number, 2753 in decimal system. Since it is in decimal system, we say r is 10, the radix is 10. Now we will first go and calculate what is the 10's complement of this number. So since the number has 4 digits, we say n is 4, and now we'll subtract this number 2753 from r raised to n. Now r is our radix, that is 10. N is the number of digits in our original number, that is 10 raised to 4, and so we have the number 10,000. And so 10,000 minus 2753, that is 7247, and this 7247 is the 10's complement of 2753. And now one thing we can observe, that the original number, and our original number is 2753, and when we add it to its 10's complement, we got the 10's complement as 7247. So let us add it to 7247, and when we add it, obviously we'll get 10,000, and that is the reason this is called as the 10's complement, because we have subtracted the given number from 10 raised to the power 4. In general, if we have a n-digit number, let us say that number is d, and we want to calculate the radix complement. So the radix complement is given by r raised to n minus d. Let us compare it with the example we had. We had here r raised to n. R raised to n was 10 raised to 4 minus d, the original given number 2753. But if d is equal to 0, supposing we see that our original number is 0, then the subtraction will become 10,000 minus d, which is 10,000, and we keep only 4 digits from the left, so we'll keep these 4 digits, and we'll discard the 1 which is on the extreme left. This will give us 0, and therefore there is only one representation of 0 in the radix complement system. How do we obtain the 1's complement? Let us consider a number 2753. Here radix is 10, and we will calculate the 9's complement of this, that is r minus 1's complement. So the 9's complement of this will be 10 raised to 4 minus 1, which is 9999, minus 2753, which is 7247.